In the previous section, we developed a Windows VI on a PC that acts as a user interface and communicates with the host VI on the RT target. By the end of this module, you will be able to transfer latest data between the host and the FPGA using user-defined I/O variables. In this section, we're going to talk about another method of transferring latest data. Now this method, it's usually only used if your host VI is running on an RT target that's already using something called the NI scan engine and also using FPGA. So one example of an RT target that might use both the NI scan engine and the FPGA is Compact Rio. So if you're using a Compact Rio and you're using some FPGA VIs, but you're also communicating with some of your modules using the NI scan engine from your RT VI, that would describe a use case where you might be able to use this method. So what is the scan engine? Real quickly, the NI scan engine is a way that an RT VI can access the I/O on the C-series modules without having to do any FPGA programming. And the way that the NI scan engine works is it periodically updates the values of the I/O from the modules and it stores it into a memory map. And then the RT VI can access the current values of that I/O by using something called an I/O variable. So this is discussed a lot more in the LabVIEW Real-Time 1 class. So you can refer to that if necessary. So if this describes what you're using something like a Compact Rio, and you're using both the NI scan engine and also the FPGA, then you can use something called user-defined I/O variables to transfer latest data. So one thing about those is if you're using these, you must have the NI scan engine installed on your FPGA. If you're using an NI scan engine, it's actually going to take up some resources on your FPGA. And also when you're using user-defined I/O variables, they're unidirectional. So each variable that you create only communicates in one direction. So for example, it might only communicate from the FPGA to the host, and you would need to create another one to go from the host to the FPGA. So some use cases for using user-defined I/O variables, they're very similar to the use cases for programmatic front panel communication. So again, they're only going to be updating the latest data, so you can use them for things like configuration or updating a current set point and things like that. However, because you're already using the NI scan engine, the user-defined I/O variables will also be able to take advantage of the timing and synchronization of the NI scan engine. For example, they will help you to be able to transfer time-coherent sets of data. So some disadvantages, if you use user-defined I/O variables, that means you're going to have to install the NI scan engine. And the NI scan engine is going to use up some of those FPGA resources. Also, the rate that you can update the user-defined I/O variables is limited by the specified scan period of the NI scan engine. To create user-defined I/O variables, what you'll need to do is right-click the chassis item in your project and go to New, and then User-Defined Variable. So notice when you do that, you'll see that there is a container for user-defined variables, and all your user-defined variables will be contained within that container as you're adding them. So in this case, we only have one user-defined variable created, and that's the FPGA to host square wave item. And we will use that variable to transfer the latest data. So here we see the configuration window when you try to create a user-defined I/O variable. First of all, you want to give it a name, and then second, notice that the variable type is I/O variable. You'll also need to set the direction. So in this case, we want to use this to communicate from the FPGA to the host VI. If we wanted to go from the host to the FPGA, we would have to change the direction there. If you're using user-defined I/O variables, you can synchronize your writes and reads with the scan engine. So if we take a look at this graphic up at the top, we kind of see what the scan engine is doing. So let's start at the beginning here. So first, we're going to be doing a scan. So during that blue block, what the scan engine is doing is it's updating all the latest values of the I/O variables for modules and also your user-defined I/O variables. So notice that underneath that, we see a picture of the scan clock. So notice during the scan clock is low. After the scan completes, then the scan clock goes high, as you can see, and that's the point that you would do all your application logic on your FPGA VI and also on your host VI. Okay. So let's say the scan period is 10 milliseconds. So at the very beginning of that 10 milliseconds, we had the scan in blue, and then the rest of the time after that is spent doing application logic. Okay? So from the beginning of the scan period till the next one, let's say 10 milliseconds has elapsed, then we're going to do another scan, which is shown here in blue. And you'll see that the scan clock also goes back low. Once that scan is complete, then the rest of the scan period is done doing application logic, and you'll see that the scan clock went high. Okay, so let's take a look at our FPGA VI. So in your FPGA VI, notice in the first frame of that sequence structure, we have something that's reading the scan clock. So at the very beginning of this FPGA VI, we don't want to start the FPGA VI until the scan clock is enabled. So here we're just reading the scan clock and waiting for it to be enabled. Once it's enabled, then we're going to finish the first frame of that sequence structure and move on to the second frame. So let's take a look at the second frame now. We have a while loop here, and then notice in the sequence structure inside the while loop, that first frame, what we're doing is we're waiting for a rising edge. So notice that's a scan clock method. So if you look back at the top, you'll notice when the scan clock is low and when the scan clock is high. Okay, so here we're waiting for this scan to finish, so we're waiting on the rising edge. Okay, so once that rising edge happens, we're going to go on to the second frame. And in the second frame, that's where you can do all your logic, and this is when you can update the values of that user-defined I/O variable. So during the next scan, those values will be updated in that scan. The other thing I want to point out is on that scan clock item over there, in the method, there's also something called missed falling edge. So for if some reason your logic in the second frame took too long, if you miss the rising edge of that next scan, then you'll be notified by your scan clock method right over here. So on this slide, we're going to move from the FPGA VI now to the host VI. So notice on the host VI, one advantage of using these user-defined I/O variables is you can also synchronize your host VI with the scan engine. So if we look at the bottom here, we have our regular code where on the host VI, we're opening up a reference to our FPGA VI and running it. And then on the bottom, we're just monitoring that missed falling edge indicator just to see if we missed any edges and things like that. And if we look at that top loop, notice that we have a timed loop. So if you have a timed loop in an RTVI, what you can do is you can double click that input node and then you can synchronize that loop to the scan engine. Okay, so notice that the input node up there says scans, and then in that first element you see kind of a synchronized text. It actually says synchronized to scan engine. So what this means is every time there's a new scan, this time loop will do another iteration. So the iteration and the rate of this time loop is synchronized with that same scan engine that we talked about in the last slide. So as you can see here, the updates on our FPGA are happening at the same time as our host is reading it. And you notice that we see the user-defined I/O variable right there in the middle in red. So using user-defined I/O variables, we're able to take advantage of the synchronization with the scan engine. Now you can transfer latest data between the host and FPGA using user-defined I/O variables. Next, we will describe how DMA FIFOs transfer buffer data between the FPGA VI and host VI.